Okay, so we'll go ahead and get started. So where I stopped last time is I was talking about this idea of displacement, velocities, distances, that sort of thing. So what I want to do is continue on this discussion, but I want to get a little deeper into it. So what we need to do is start kind of representing this mathematically a little bit to start to give us some idea of how we want to map this out and how we want to start doing mathematical models of these kind of things. So if you'll see that in this first graph here, I've got position versus time. So notice that I have position in kilometers on the vertical axis and time in seconds. Looks like each division is 1/10 of a second on the horizontal axis. Remember, we can pick our axes to be whatever we want them to be. So if we choose, because it's convenient, that whatever this motion is that we're describing, we're going to choose to start in this first graph at 0 time and 0 position. So whatever position we started at, we're going to call that 0. And as soon as we start our stopwatch, we're going to call that time 0. So what you notice is that whatever this spherical cow is that's moving, after 0.1 seconds, it's gone 1 kilometer. After 0.2 seconds, looks like it's gone 2 kilometers, et cetera, et cetera. This is pretty easy to follow up until this point. So this looks like at about 0.4 seconds, we're at about, I don't know, 6.5 kilometers thereabout. But then notice what happens. The distance in the next 0.1 second that we're measuring from 0.4 to 0.5 goes from 6.5 all the way back down to 0. So it's important to understand what this represents. This is a position versus time graph. So our position is changing. Notice that as time moves to the right, that's our positive direction. So we're just adding time. Remember, we started at 0, we're just going to add time. So as we add time, the spherical cow moves further and further away from the origin, as indicated by the position going positive. Once we get to this point here, notice time does not stop. Our next point that we're measuring is certainly to the right on the x-axis. It is certainly advanced in positive time. However, the position has decreased. So this looks like our spherical cow is now moving in reverse of whatever we chose to be the positive direction. So this is that kind of displacement argument. I want you to notice something here. Remember, displacement is our final position minus the initial position. So if we look, our final position here is exactly on the axis. So that's going to be a position of 0. Our initial position was 0. So that means our total displacement is 0. But we can clearly see that the distance traveled went from 0 to 6.5. So that'd be about 6.5 meters or kilometers, I guess. And then back down to 0. So that's another 6.5 kilometers. So the total distance looks like about 13 kilometers, but our displacement is 0. Another thing that I want you to notice about this is actually going to be a little bit more important kind of concept. It's one of those things that you saw and you learned in algebra. and you kind of figured out how to do by rote, but nobody really explained to you what it was. And that's calculating the slope of a line. You calculated, when you did slope, you learned this formula of rise over run kind of thing, right? You counted how many places you moved in the y-axis, and you divided it by how many places you moved in the x-axis, and you got what's called the slope. And you might have figured out that slope is kind of an indication of how steep this line is. That's only part of the story. The steepness of that line, the slope of that line, represents something more fundamental. It represents something interesting to us in physics. Remember, the other day I was talking about the concept of velocity. Velocity is distance per time, or delta D over delta T. That means change in distance over change in time. If we think about this as an algebra 1 problem, what is the change in distance? Well, it's the final position minus the initial position. I'm sorry, there's your position there. Well, that certainly looks like the y-axis. That certainly looks like the rise in our rise over run calculation. Our delta T is our run. So here we have our rise over run gives us the slope. So intuitively, we can think about what happens if we cover more distance in less time. For example, if it only took us 0.2 seconds to get up here, then our line would be much, much steeper. Our slope would be much higher. So what that tells me from a physics standpoint is that now that concept of slope on a linear graph means something. Slope of a line in physics means it's change. So if we're graphing distance and time, then the change in distance per unit time is the velocity. That's the very definition of velocity, change in distance over change in time. The slope of this line is the velocity. It gets a little more interesting when you expand that out and we look at this graph. All three of these graphs represent the same motion. This is the same spherical cow under the same time conditions. However, we're looking at different things. In the top graph, we're looking at position versus time. And we figured out that the slope of position versus time is our velocity. Well, we could certainly calculate the slope of that line. Now, because this is linear, I hope you guys will remember enough from Algebra 1, that because this is linear, it's not curved, that slope is going to be constant. So no matter where we measure the slope of this line, whether it's here or up here somewhere, that slope is always going to be the same. So if we start mapping the slope, which remember we said was velocity, and here it shows up again, kilometers per second. So distance per time is our velocity on the y-axis. Look what we notice. That our velocity starts at 0 because we're starting at the origin, 0 distance over 0 time. Then from 0 out to 0.2 seconds thereabouts, we have a constant slope. Then suddenly the velocity goes in the negative direction, but time keeps going. So notice there's what looks like a discontinuity here. Remember, we're not measuring distance versus time here. We're measuring velocity versus time. So what this tells me is I'm traveling at a constant speed up until this point, and then I travel at a constant speed in the opposite direction because now I'm negative. Remember what I said the other day? In physics, negative signs mean direction. So that's all we've done here. We can take it a step further. If we look at our speed versus time chart. So this is our velocity. Or speed, I guess. Over time, look what we get. It's constant. So what that tells me, this is something called acceleration. Acceleration is the change in velocity over the change in time. So it's this graph over time. So this first graph is this graph over time. This graph is this graph over time. This graph is this graph over time. So this tells you a lot. This tells you that you're moving in a positive direction at a constant speed. Then you turn around and you come back to where you started were at a constant speed. Now those speeds may be different because the slope of the line is different, and that's notated by the fact that this goes up to like, what was that, 10, 12, something like that. Yeah, they didn't really draw that very well, but that should go down to an even lower value. So you can see that we did not change the rate of our speed change. Once we set a speed, it was the same. So if we set a speed of 60 miles an hour and we drive, it'll always be 60 miles an hour. So we get a flat curve for velocity versus time. And then that change in velocity, since we started at 60 and we ended at 60, we didn't change anything. We didn't accelerate. So our speed versus time, or our acceleration, is 0. It's a constant. I'll show you some examples when I switch to the whiteboard where that gets different, and I'll show you a little bit of calculus too. That is a fun airport to land at, St. Martin. Okay, so this is an interesting little graph. This is just some subway in Sao Paulo, which I've never been to, or in Brazil is awesome. Notice that we're looking at the velocity and the acceleration vectors here. So imagine this train is coming towards us. And so we have this green line that represents velocity. So its velocity is certainly positive. But it doesn't do us any good to just continue on through the station, going at whatever our cruising speed is, because that really suck for the people that want to get off or the people that want to get on. People want to get off are going to have to learn how to tuck and roll. People that are going to get on, sucks to be them. So we need to stop. Well, it's a problem to just slam on the brakes and stop instantaneously. So we have to slow down. In other words, we have to decelerate. So our velocity, while it remains forward in this case, remember we're going to pick that positive direction to be that green line. Our acceleration vector, our change in velocity over time, is going to be negative. So we're slowing down. That's kind of what we want. Well, what's going to happen if you think about this mathematically, try to imagine this dynamically, as this acceleration vector gets big, this velocity vector is going to get small. When the two are equal to each other, now we've stopped, right? Because we're going forward as fast as we're going backwards, or as we're changing our direction backwards. So we're going to slow down. Now, if we continued that trend, what you would see is that the direction of those arrows would change. Imagine taking a baseball, throwing it in the air, straight up. It's going to travel up until a certain point. It's going to get at the top of its arc, It's going to change direction. It's going to come back down. You can do this just sitting at your desk right now. Just take a pen or a pencil or something and just kind of toss it up in the air and watch what happens. You're going to see it go up, but it's going to get slower and slower and slower till it gets to the top of the arc, and it's going to stop. For just a fraction of a second, it's going to have zero velocity because its upward velocity is going to equal the downward acceleration due to gravity. It's going to appear to float there for a fraction of a second, and then it's going to start coming back down, increasing velocity as it goes because acceleration is taking over. This is exactly what's happening in this diagram, except we're talking about this forward and backwards motion instead of up and down. But remember, I'm a physicist. I don't care if up, down, left, right is positive as long as I'm consistent. In this case, it would be dumb for me to pick the positive direction of the motion I'm trying to measure as towards the top of the train because it doesn't tell me anything. I'm only interested in what the thing is doing along the track. So I'm going to pick the direction of motion to be the positive direction. That makes sense. That's the motion I'm interested in. This is going to be useful to us when we start doing inclined plane problems. So here is another kind of example of that. I have a car and it's speeding up as it moves towards the right. So it's got a positive acceleration in our coordinate system, right? It's getting faster and faster and faster as it moves. That means that delta V over delta T is increasing. So we notice our vectors here. Their velocity increases, our acceleration is increasing in the same direction. So that's going to get bigger. This is the slowing down. We're going this way, but we're going to decelerate to the left. Diagram C here is exactly the opposite of diagram A. The only thing that's changed is the direction. So if we were to try to graph this, all we would do, if we pick to the right as our positive direction here, as long as we're consistent, it just means this is travel to the left. So that means our direction would be negative. So what? Time is still going to be positive, right? It makes no sense to look at something and start our timer at -5. That doesn't make any sense, -5 seconds. So we just kind of automatically assume that our time is 0. There are going to be times, not in this class, but much, much later in your physics education, where we're going to have to start worrying about things with negative time values. It gets really funky and it starts to talk about things like relativity and things traveling at the speed of light and it's counting for the curvature of space-time. You are not ready for that yet. But it does exist. But for our purposes, time's going to be a positive value. I'm not sure what's going on in this picture. Some horse racing thing. All right, so here is our example. Here we have some particle. Its final velocity, its initial velocity, you notice, V0, come on. Our V0 is 0, so we start at a velocity of 0. We're not moving. We end up, after some time, going -15 meters per second. So all this means is that we're moving to the left. When we started our time at time 0, we were going 0, and we stopped our time at time final, and we were going at -15 meters per second. So what's the acceleration that we're experiencing? Well, you do delta V over delta T. That's acceleration, right? So if we have delta V over delta T, our delta V is final minus initial. So -15 minus 0 still gives us a -15 meters per second. And then our time, since I didn't really give you a time, we're just going to use generic values. Our initial time was 0. Our final time is just some t. So that ends up being just whatever this delta V over t is. So our final acceleration becomes negative 15 meters per second per time. If we assume this is 1 unit of time, then times in seconds, you get a minus 15 meters per second per second. You might hear this as negative 15 meters per second squared. That means for every second that this particle moves, it gains another 15 meters per second, in this case, the negative direction, because that's just what we picked. The other place you have heard about acceleration, and we will use a whole lot in this class, is the acceleration due to gravity. Acceleration due to gravity is 9.81 meters per second squared. If you need a quick estimate, use 10 meters per second squared because the math is pretty easy to do. But I would really like you to use 9.8 unless the homework specifically says just use 10 to make it easy. Because that's going to be more proper. That's 2 decimal places. So what that means is that if you take a baseball, a spaceship, a spherical cow, and you drop the spherical cow from some height on Earth, that cow will gain 9.8 meters per second of speed for every second that it falls. So after the first second, it's traveling at 9.8 meters per second. After the second, it's going to gain another 9.8, right? So after 2 seconds, it's not going 9.8 meters per second squared. It's going around 20 meters per second squared, right? Because we've just added that. And it's going to get faster and faster and faster until it makes a smoking hole in the ground. There is something called terminal velocity that limits how fast something can fall. It has to do with air resistance, and we will talk about that later. But remember, in this case, most of the things we do, we're talking about spherical cow in a vacuum. So the cow is going to continue to fall for eternity, and it's really going to suck to be him. So let's take a look at this graph. This is kind of interesting. This is instantaneous acceleration versus 2 different time for 2 different motions. So the first graph, A, acceleration varies only slightly and always in the same direction. So notice, here's our acceleration. We start with our velocity. Oh, sorry, that's our acceleration, meters per second squared. So this is roughly gravity, right? A little more than 10. It goes up to about 20, and then it comes down to, I don't know, it looks like about 18 or something, then back up to about 20, and then back down. So this represents accelerating and decelerating just slightly. So imagine that you're driving down the highway and you get behind one of the rare bad drivers on the interstate in Little Rock. I know those are extraordinarily rare to encounter, but let's assume that we get behind one and we're constantly speeding up and slowing down. This is what your acceleration curve looks like. Suddenly you're gaining speed, then you're not gaining speed as fast, and then maybe you go backwards. You really don't want that to go to 0 and your velocity go to 0 at the same time, because that means you hit something. If we look at the second graph, though, here the acceleration varies greatly, representing a package on a post office conveyor belt, let's say. So again, vertical line is our acceleration. That's how quickly we're changing speed. So we're changing speed by 3 meters per second squared up until 1 second. At 1 second, we suddenly change our acceleration to -2. So that means suddenly we started moving backwards. Well, how can that happen? That means we hit something and we bounced off. This is if you ever listen to audio recordings of, space shuttle reentries or something, you think about fighter pilots, you'll hear about G's, pilot pulling G's, or get 4 or 5 G's on reentry of a spaceship. That's what this is. G's is a measure, it's a unit, 1 G. 1 G is 9.8 meters per second squared. It's acceleration due to Earth's gravity. So 2 G's is 2 times that. 3 G's is 3 times that. If you've ever been at an amusement park and that ride that spins you around in a circle and pins you to the wall, makes you want to puke, you're getting around 1.8, 2 G's on that. That's all. But if you think about that ride, if you're standing on it, let's say you weigh 200 pounds and you tried to lift your arm, or you tried to stand up lifting your whole body weight, let's say, normally you're lifting 200 pounds because so much weight on that thing, you'd be trying to lift 400 pounds. A little more difficult, right? Well, normally I'm not trying to stand up in that. Normally I'm just going to try to raise an arm. So the average human arm weighs on the order of 6 or 8 pounds. Don't worry about how I know that. You try to lift your arm in normal gravity, you're lifting 6 or 8 pounds, not a big deal. In the accelerometer ride thing, you're lifting, 12, 15 pounds. Not a big deal. My cat's pretty fat. He weighs about 10 pounds. So that's not a big deal. I'm picking up the kitty cat. But think about what happens if we change our velocity per second in a very short amount of time. So we have a large number over a small number. That number goes way up. So if you get something like 100 G's, that's a large change in acceleration over a short amount of time, or a large change in speed over a short amount of time. That's a big deal. If my arm weighs 6 pounds and I get 100 G's, now my arm weighs 600 pounds. Try to put a 600-pound weight on top of your arm, probably going to break bones. So this is what happens in car crashes too. When you have a car crash, it's not the speed that kills you, it's the acceleration. You hit something and you decelerate from some velocity to nothing in a very short amount of time. That's a lot of energy. We're going to talk about energy next week. So again, this little example here, we've got this box moving on a conveyor belt, gets bumped backwards, starts moving that way. So now it's moving backwards, right? Accelerating backwards. Gets bumped again. Now it's not accelerating. Still moving though. Time's still going. Things still moving. It's just not accelerating. So this velocity curve would probably be a vertical positive slope. And it looks like we accelerate a little bit, move straight, accelerate a little bit more, constant. And then, oh no, we stop. Move a little bit more. These kind of graphs are not really all that hard. We just have to think a little bit ahead of the curve here and really consider what's going on. There are a couple of these on the homeworks, so take your time. I'll tell you what, let me try to switch over to the whiteboard. Come on. No. Well. You guys are still seeing the slideshow, right? Man, this is still not working the way I want it to. Now you should be seeing the whiteboard, right? Let me take this. Here. Here's my whiteboard. So let's do something here. Let's have car. And let's say that my car is traveling at, I don't know, 10 meters per second to the right. Then we're going to say after, and we're going to start the time at 0. And then after, let's say 2 seconds, we have to slow down. To 5 meters per second. If we want to make a graph of this, we start with our position versus time graph. So if we make divisions on this, let's say that this is 0.5, 1, 1.5, 2.0, and their distance we'll say is 2, 4, 6, went up to 8. We start at the origin. So we started from time 0 and went to some time. So after, so we're assume we're not accelerating. So we start at a velocity of 10 meters per second. And we look at what's happened after 2 seconds. If we're traveling at 10 meters, for every 2 seconds. Well, 10 meters per second, right? Sorry, let me do that again. Traveling at 10 meters per second. We want to know what happens after 2 seconds. So we just do a unit conversion. We get a 10 meter per second, and we want to go to meters because we want to know how far we went. So we need to do times 2 seconds. Seconds cancel. So we've gone 20 meters. So after 2 seconds, my distance is going to be up here at 20. So it looks something like that. Notice that our slope is positive, meaning our acceleration is constant. So our acceleration chart, we look at velocity over time. Our acceleration chart, well, that looks like 10 meters per second per 2 seconds, looks like 5 meters per second squared. So our acceleration looks like this. Our velocity is 10 meters per second over the amount of time, but it didn't change. So our acceleration curve, it's constant. The slope is 0. I'm going to show you something here. This is not required knowledge for this course, but I want to give you a general idea of what's going on. Remember, when you did algebra 1, you learned this: y equals mx plus b, your slope-intercept form. Well, the thing we were interested in is this. That's our slope. And remember, there were a lot of ways you could get that. But the way that you probably learned how to do it is you said slope is rise over run, like we already talked about, right? Rise is the change in y, run is the change in x. So we got a slope. There is an easier way to do this. So let's say I have some linear equation and I want to find out what the slope is. I could certainly go and find numbers, right? I could certainly find my y-intercept. I could find my x-intercept. I could plug them in this equation and I could find out what that is. Well, the easier way to do this is with calculus. You can take what's called the derivative, y prime, sometimes we call it. Some call it dy dt. It's not like delta y over delta t, right? If you take the derivative of this thing with respect, actually it should be dx, because we're deriving with respect to x. We look at the rate of change of each of these things. Well, mx, if you take the derivative of that, looks like m. The derivative of b, it's just a constant. Turns out that derivative of any constant is 0. So that means the derivative of this line is m, which is your slope. So that means if you take the derivative of any curve, you get its rate of change. If that curve, if that equation represents a line that is distance per time, and you take the rate of change of that, you get velocity. Pretty simple. Watch what happens just as a matter of example. Here's our distance in time. We're going to start at 0, 0. What if we get something that looks like that? It's nonlinear. We get this curve. So wherever I take the slope of this line, here, 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 it's going to change. That means that we have a non-constant acceleration. That acceleration, the way I've drawn it, happens to be squared. So if we take velocity over time, instead of getting a straight line, what our velocity over time here looks like is this. That means our acceleration is changing. What does this look like in reality? Well, if we were to expand this first one, left and right, you get a parabola. If you remember back to algebra 1, the basic form of this is y equals x squared. So anytime you have an acceleration that grows by a factor of a square, it's probably going to behave the same way. Doesn't really matter. Now, like I said, this is kind of above and beyond what I expect you to know in this course, but I think it's important to see this because it's going to show you kind of where you go with this. And it shows you the value of the mathematics. As we dig deeper into this, we're going to find that mathematically, we're not going to really need to graph things. Graphing them early on is going to help us understand what's going on mathematically. But as we move forward, understanding these concepts is going to help you build the formulas. Physics is one of those things that a lot of my students come to me And they have a real problem where they want to do physics the way they've done mathematics, where they just kind of memorize a formula and plug numbers into it. If you do that with physics, you're going to have a bad time. You need to understand what the equations mean. As a result, I am going to do things in physics and on tests where I am going to ask you to solve things symbolically, where I may give you an equation and I may say that you've got something so we might have some particle and I can describe its motion as x equals x naught plus v naught t plus 1/2 at squared, where v naught is your initial velocity, x naught your initial position, t is the time, and a is the acceleration. And I might ask you to find an expression, find an equation that expresses the acceleration of this particle at any given time. This shouldn't be that difficult to do. It's just rearranging it algebraically. But I'm going to tell you that if you know how to do that, yeah, it's going to be hard. It's going to be a little tedious. But if you figure out how to do that, do the algebraic manipulation first, just like I'm going to ask you to do on tests. When it comes to actually solving real problems, solve it symbolically, get to the variable you want, then put your numbers in there. You're not going to lose zeros. You're not going to lose decimal places. It's a whole lot easier for you to deal with this kind of thing. No, come on. So, yes, I know what I'm viewing. So I think that's where I'm going to stop for today. Does anybody have any questions before I stop this for today?
No, I'm good.
All right. I am going to, when I get back to my office, I'm going to post a link. I'm starting to share all these videos on a YouTube channel that I've set up. So you'll have a one-stop shop for them instead of having to go and copy the link and copy the code to get in and view the video. You'll be able to just go to the YouTube channel and watch them at your convenience and not have to worry about the logins and things like that. Okay. I have also started on Blackboard. I put in a placeholder for the grades for the first week of homeworks. You'll notice that on week 1 of homeworks, that there are 2 assignments. They're both pretty short. That's what your homework's going to look like. Typically, you should have already started on week 2's homeworks, and you're going to have a couple of short assignments there. That's the way I intend to do them going forward, is instead of one giant homework assignment, you're going to have 2 or 3 little smaller things. It's easier to work on them in chunks that way. And then for the entire week of the homework grade, I'm just going to take the average of all that week's little mini assignments. And that's what I'm going to post as your grade on Blackboard. Okay. So having said that, I think that is enough for today. I will be in my office this afternoon for probably another hour or so, and then I'm going to the house. But remember, if you need help, reach out to me and I will help you. All right. See y'all next time.